How long it takes?
6 years?
Oh,
No, I don't think it's that long. I think it's more like 6 months.
just 6 months.
That's more manageable time to get to Mars. Okay.
6 months sister.
Right. Next lesson now. So this is the last lesson in fields. Not as long as the last lesson.
What's this? Keplers Law.
Keplers Law.
Kepler.
Do you know this dude?
Nope. Never heard of him.
Never heard of him. Alright. Got this?
Okay.
So like everything in physics, if you're going to have your name beside laws, you're going to need at least 3 of them.
Really?
Newton's laws,
Really?
thermodynamics laws. Yeah, all these laws come in 3s. So Kepler likewise has 3 laws. Okay?
What
So
about the other laws that we learn?
you can revise them.
Lenz's law.
Yeah.
Does it come in 3?
Yeah, Lenz's law, not Lenz's laws.
But this one says
It's
Kepler's
law.
And then
law.
think about your hand laws. You have right hand grip, left hand, and right hand.
But
See, if you want to make a name for yourself in physics, you need at least 3 laws. Okay?
That's the rule.
oh, okay, that's why this
Newton's
guy.
making this up.
That's why this guy does not have a name. He only has one law.
Oh, well, if you're only going to have 1 law, it needs to be a really good one. Okay? Right. So, Kepler's first law of his trade.
The law that states when you jump off a building, you die.
Nearly as basic as that.
First law.
Okay, so Kepler's first law.
So there are more than one.
Guess how many there are?
3.
Correct. Kepler's first law states that bodies in orbit of the Sun or other large masses will move either in either a circular path or elliptical path. And if you don't know what elliptical looks like, that's elliptical. It's not quite circular.
Of the sun, I don't know.
Or other what?
Huh?
Or other large masses. I mean, it doesn't have to be the Sun. It could be the Moon around the Earth. The solar system around what?
Will it be a wrecking ball?
I think there'd be other forces bigger than gravitational force that would kind of dictate its movement. Now, important thing to note about the elliptical path. In fact, the Sun is deliberately drawn not in the center. So when it's in an elliptical path, the Sun is not the center of the ellipse. You don't need to know in this course where exactly it is, but it's enough for me to say that in an elliptical path, which is this shape, the Sun does not lie in the center of the ellipse. It's only in the center if the path was a circle. Okay? Have you seen this word before? Elliptical? Ellipse? Do you know this word? Ellipse is this long shape.
I know physics.
I know eclipse.
Okay, fine. Next.
We should draw too.
Oh, you should draw it, yeah.
How about not proving?
Huh? This can be proved, but we don't. The proof is way too difficult for us to do. But it can. My point is, you can prove from this formula that the only orbits the planet can take are circular or elliptical.
Not a square.
No, no. Well, that's now. I know that seems like a silly statement to make, but at the time, people didn't know for certain what type of path it takes. So people thought it was a circular path because it orbits, but we weren't sure, or they weren't sure, if it was exactly a perfect circle. And the answer is no. It can be circular or elliptical. Okay. Right. Continue.
Then if
Yeah.
Then if it's on the other side, it will be very hotter.
In fact, for Earth, the temperature difference is not noticeable. I know it seems like this part should be warmer and this part should be cooler,
Yeah.
but it's not. The environment is able to regulate the temperature so it stays constant.
Because it's a big difference.
Well, this is going to be a bit exaggerated. I'd say the difference is maybe 5%, I don't know. It is a big difference, but the Earth is still able to regulate its temperature globally. So the reason that it's hot in the summer is not because the Earth is nearer to the sun, because when it's hot in the summer here, it's cold down in Australia, down south. So it's just because the Earth is tilted forward or away from the sun. So in fact, there's no noticeable temperature difference here or here. Yeah. Now there is. Well, there is a difference, but what I'm saying is the Earth, its environment can regulate the difference. So, for example, if it's a little bit warmer here, the Earth's atmosphere and natural environment can do something to reduce the heat. And likewise, like the environment on the Earth has been adapted to match these conditions every year. Okay? I mean, in the past, there was lots more heat. I can't remember. In the past, I think there was maybe more heat coming from the sun, or I can't remember exactly what. But throughout the history of the Earth has been able to roughly maintain a constant temperature despite its position changing.
Because of the ozone layer.
Yeah, many factors. Ozone just being one of many factors. So the Earth can keep its temperature roughly the same for a few billion years until humans come along and then we screw it up.
Because even in the news.
With our CO2 and the likes. But previously, before humans were driving cars and the likes, the Earth had a good time keeping its temperature balanced.
Now they're saying the people are trying to, like change climates, and it's not the natural. The climate's changing. It's not natural.
Yeah, well, it's still, there's many things we don't know about the climate, but one thing is certain, that it is changing. Now, whether the reason is man or the reason is something else, that depends on who you ask. But it doesn't really matter what the reason is. If the climate is changing, you'll have to do something.
Now they have technology to get rain and these things, clouds.
Yes. No, there are things to be done. Okay, so Kepler's second law states that the periodic time squared is proportional to the average radius of the orbit cubed, or in other words, t squared is proportional to r cubed. Now that formula is not particularly helpful. We can actually give it as an equation which is much more useful. Mathematically, as a formula, we can get t squared equals 4 pi squared over gm r cubed. So if you know the orbiting radius and the mass of the sun, you can know the time for the orbit. And bad/good news, this proof is on the exam, and in fact, because of that, the formula is not in the formula book. Let's prove it.
T squared.
Can remember it.
You think that, but you'll be remembering it when you're not doing your homework and playing Minecraft. I don't know.
No.
Oh, sorry, World of Warcraft.
No.
FIFA
No.
29 or whatever it's at now.
No.
What number's FIFA at?
16.
Losers. Right. You got this? I want to do the proof now.
No, neither.
Yes, 4 pi squared. The square will only be pi, right?
Yeah. So I repeat, the proof is on the exam. And in fact, in the exam, they'll ask you to prove it, and they won't even say prove it. What will happen in the exam is they'll give you a question which requires this formula. So before you can even answer it, you're going to have to prove this formula. So the question will give you information, and it'll ask you for what is the orbit in time, but the only thing it'll tell you is the radius and the mass of the sun or planet that it's orbiting. So you'll have to prove this formula. Now, I don't know if you actually have to prove it. I think the marking scheme might allow you to get the marks if you memorize it, but if you memorize it, you have to say by using Kepler's second law. But there's a possibility that the exam question could explicitly say prove this formula, because it is something that could be on the exam. So let's prove it. The proof is not too difficult. So we have a mass m and mass m, and it's orbiting like this. So we know that F equals g m m over r squared. But we also know that F equals m omega squared r. So by making these equal, we get g m m over r squared equals m omega squared r. So you can get then that g...
F is equals to mv squared r.
Yeah, or m omega squared r. You have two formulas.
I thought it was v squared over
It
mv
is.
squared over r.
It is. Or m omega squared r. There are two formulas.
Okay, I thought I saw v there.
Glasses, dude, glasses. So we can cancel the small m's here, and we can get gm equals omega squared or cubed. Or we can get 1 over omega squared equals, sorry, let me think. I want to get it exactly like this, so I need the gm to be, yeah, I was right. You can get 1 over omega squared equals 1 over gm or cubed. But what does omega equal? Do you remember? It's 2 pi over t squared equals 1 over gm or cubed. So then we can get t squared over 4 pi squared equals 1 over gm or cubed. And finally we get t squared equals 4 pi squared over gm or cubed. So this is Kepler's second law. So this is how you get the result that t squared is proportional to or cubed. This is the proportionality constant. Not crazy difficult proof. Again, we use Newton's law and the circular motion formula force.
Just use 2% work into
Exactly
the
right, 100% exactly right. And although if I had, I don't know actually if Kepler, see I think Kepler was before Newton, so this Kepler would have had a much more difficult job getting this formula without Newton's work. And also, again, the formulas for circular motion would have been done by Newton, so again that was before Newton. So I know for us it seems easy because we have Newton's mechanics, but for Kepler at the time he did not have Newton's work, so he had to figure this formula out from just looking at some data that he had. You know?
But he could have discovered the Newton's law by himself.
He could have, but I don't think he did. I suppose he could have, and maybe, I don't know, maybe if he had more time he would have. Yeah. But I know it seems easy proof now for us. We just use two of Newton's formulas. Yeah. But this existed before Newton's formula. Except, I think when Kepler discovered the formula, he originally had it like this, because he had no idea of knowing what the constant was, because, of course, Kepler didn't know about Newton's big G, because Newton wasn't around yet. And of course there would have been no way to know what the mass of planets were at the time. So his formula would have been more like this with the proportional symbol. It would have been, it's very easy to know, even back in 1600s, it's very easy to know the time it takes for something to go around the sun. Like, for example, the Earth, we all know, is 365 days. And also, using a telescope, it's easy to know how far away you are from the sun by using some basic trigonometry. So he would have just looked at the data and he would have noticed that if you square the time and if you cube the distance, that they're in proportion. Okay, so for example, he would have looked at the radius of the Earth and the time taken to go around it, and he would have looked at the radius of Mars and the time taken to go around it, and he would have noticed that t squared is in proportion to r cubed. That if you double r cubed, you would double t squared. So for us, it's more convenient to use the formula because we can calculate stuff then. Okay, you got this proof? Right, so Kepler's third law. I'll have to give you a picture to explain it, but Kepler's third law states that the area swept out by an orbiting body per unit time is constant.
The area.
Swept out. Yeah, I'll explain with a picture. Only if it helps you. Let me explain what this means. So, in this picture here, I'm taking the unit of time to be 1 month. It doesn't matter what unit of time you choose, but it should be quite small. So 1 month would be the limit. You want to be using smaller units than a month, like a week or a day, or even a second. So what Kepler's third law states is that if you look at the motion of the planet over 1 month and draw a triangle, this area here will be the same as the area in any other part of its journey over the same period of time. So if you look, maybe this is January. So in January 1st to January 30th, you look at how far the planet has travelled, you draw the triangle, you get the area. And then 6 months later in July 1st, and then July 30th, you look at how far the planet has travelled, you draw a triangle and you measure the area. Although this is closer to the Sun, you think that the area should be less because the distance is smaller, but in fact it travels more than what it travelled here, and in total the result is the areas will stay the same. So this area and this area, or anywhere else, is always equal. So that's what I mean by the area swept out per unit of time is constant. So this area and this area, A1 and A2 are equal. Huh? It is. I mean, it's not something you would have guessed as a rule, but it's true. And again, Kepler would have come to this conclusion by looking at the data that he would have about planets and their orbits.
This theory has been proved.
Oh yes. Yes. This is definitely true. Definitely true. Okay, so write this down. This is Kepler's third law.
To draw this.
Yes.
You sure?
Only if it helps you understand the rule. You know what, draw it. It's a circle and 2 triangles. It's not going to kill you. You might kill KJ now. Got it? You drew it? don't just sit there looking like you don't know what's going on. Draw it while you're waiting. Make yourself busy. Look busy.
No, it doesn't help me. I always say that.
I don't care if it helps you. Look busy.
Okay.
Yeah. When I worked in McDonald's, one of the things someone told me was, always look busy. Even if you have nothing to do, look busy. If you have nothing to do, wipe a table, wipe a wall. Just never let the boss see you standing there going. Alright? So again, I'll give you the same advice, Karar. Look busy in class, okay? I don't want your teacher to look at you and just see.
That's a nice one.
But if you have done
Doesn't matter, look busy, clean it
busy,
again.
look busy.
Look busy. Alright.
Grab the pen and do it.
you look at me.
I'm unbelievably busy.
Maybe with your phone, you can practice it.
Bad busy. Okay. Next. Yes, continue, you got this?
Yep.
Right, so there's just a little bit of vocabulary. So we have something called a geostationary or parking orbit. Does anyone know the meaning here? A geostationary orbit? So a geostationary or parking orbit is an orbit around the Earth or other masses which has a periodic time t of 1 day. So what that means is if there was a satellite in a parking orbit around the Earth, it means its time to do one orbit around the Earth is 24 hours. Now the reason for that is because if you think about it as a picture, I'll just draw it here for you. Here is you lying on the ground on the Earth and you are looking up into the sky. How long would it take you to go around once?
1 month.
No, come on, don't make me get angry.
Let's see.
No, listen. How long will it take you? You are lying on the ground. This is easy to imagine. Okay? You've just been punched in the face. You're lying on the ground and you're looking up into the sky. How long will it take you to go around the Earth once?
30 seconds.
Not 365.
3 seconds or 2 seconds.
Oh my goodness. You are all being so stupid right now. 24 hours. No, don't look at me with those stupid faces. Seriously. This is not. What happens after 24 hours? The Earth rotates once.
Yeah, but
Yeah, but what?
you said as if you will be moving over.
I'm not moving. I'm standing here. The next time I am here will be 1 day later. I'm moving right now. You can't see me moving because you're moving too.
Exactly. But you said it is as if the body was moving or something was moving. That's why he said something.
Don't, KJ, don't be ridiculous now. Look, here's the Earth here, okay? Right, so here am I on top of the Earth, alright? How long until I'm here again? Not until another 24 hours has passed and I'm back here. Yeah? Why is this confusing people?
No.
Is it confusing you?
No.
You're looking confused. Why are you confused?
No, maybe.
Okay, great. You're not confused. You know what I'm saying? Do you? Are you sure? Yes? Now, I don't know if you know what I'm saying. 24 hours is how long it takes you to end up in the same position you were. Yes, true, on the ground you are not moving, but the ground is also moving. Everything is moving. Yeah? So it'll take you 24 hours. Now, if you were looking up in the sky and there was a satellite right above you.
But you can't see it.
Yeah, no, if you had a telescope you could see it.
Okay.
Yeah. You had a satellite right above you, or if it was GPS you can detect it. If the satellite also takes 24 hours to go around the Earth, then what will happen is that the satellite will always appear to be above you. So when the satellite's time is also 24 hours, it makes the appearance that the satellite is fixed in the sky. This is how GPS works. The GPS satellites have a time of 24 hours, and this means that the satellites always look like they're in the same position in the sky. So they act as fixed points in the sky for reference and calculations. So this is why we also call it a parking orbit. It's like the satellite is parked in the sky. Okay.
Oh,
Um,
number down.
yes.
Definition.
Now, of course, it's one day on Earth. On other planets, it won't be 24 hours because they will have different lengths of a day.
At the down?
The definition.
But they say if you go in space, you won't age.
No, you'll still age. Sorry, bad news for you. Did you write this down, KJ? The definition box.
Not in my head. Yeah.
Okay, got this? Right, so, let's have, what's on?
Do you have to? No, that's
No, just the
yeah.
box, just the box. Right, so a small satellite is in a parking orbit around the Earth. How far is it from the surface of the Earth? Note that the radius of the Earth is 6371 kilometers. Right, so I'll draw what we have here. What we have our Earth, and we have our satellite in orbit, and we know that the time here is 24 hours. So my question then is, what is the required radius here for a time of 24 hours? Right, so if we know that t is 24, then we know that,
Speed is different. The speed would be different.
what do you mean?
The rotating speed. You know, like the speed the Earth rotates.
Ah, what are you telling me? Break it down for me.
Like this is the Earth, for example.
Yeah,
If you are here,
yeah.
this distance,
Your speed, or your distance, well?
your distance would be different.
Yeah.
This has a
Yeah. But it'll still take you 24 hours to loop around.
time frame was a
Yeah.
different.
But we're not looking at the surface, we're looking out here. And yes, different ores will create different speeds. Right, so t is 24, but t is 2 pi over omega. So omega is 2 pi over t. Omega is 2 pi over t, which is 24 times 3,600. So it'll be a tiny number of 7.27 times 10 to the minus 5 radians a second. Now remember that from circular motion A equals omega squared or. Yes? Or if you want, you can say F equals m omega squared or. Actually, you know what? We can just use Kepler's law here, because we want the or and we know the t. So actually, yeah, I don't even need to do all this. I can just use Kepler's law. Kepler's law says that t squared equals 4 pi squared over gm or cubed. Do we know the 4 pi? Yes. Do we know the gm? Oh wait, do we know the mass of the Earth?
Yeah.
Yes.
Did I give it to you in the question?
No.
No, then we need to go backwards. Oh, come on.
But we know it's four.
You know?
No, but I didn't give it to you in the question.
But
So
it's a formula though.
no, it's not. So we'll have to go back. I'll just write the value back in. What did I say omega was? Oh, I still have it here. 7.27 times 10 to the minus 5 radians a second. Okay. F equals m omega squared or, and F equals g m over or.
Did you convert 24 hours to
Yep.
something?
I did.
You convert it into
Seconds.
okay.
Okay, so we can have m omega squared or equals g m over or squared.
How do you check what?
The or.
How do you now remove the M?
Well, I can cancel the small m's.
Big M.
I need to calculate big M from Kepler's law and plug it in. No, I can't do that because I don't know or. Oh, rats, so do I need to give you the mass of the Earth? Rats, I do.
So we don't need to go, because this will later on.
Alright, so we'll give you the mass of the Earth then. So then, or, yeah, okay, rats. Yes.
You don't need this. This is like proving the formula.
It is, isn't it? Yeah. Back in time again we go. Right, I need to give you the mass of the Earth. You can't do it without it. What is the mass of the Earth?
5.97.
5.97 times 10 to the power 24.
Okay. So Kepler says that T squared equals 4 pi squared over gm or cubed. So that means or would equal cube root of gm t squared over 4 pi squared. Okay. And now I have to put the time in seconds again. Divided by 4 pi squared. So I got the radius here to be 4226910. That's the total distance, but we don't want the total distance, we just want the height above the surface. So what do I need to take away from this number? The radius of the Earth. Do you remember what that is? Or I give it in the question. It's 385,000,000. No, too many zeros. What's the radius of the Earth? No, 6371, sorry. Minus 6371000. So you get then the height needs to be 35,856 kilometers above the surface of the Earth. Yeah, parking orbits are very, very high orbits.
6969?
6371, isn't it?
No, 4222.
35856 4222 6910.
10.
I think so. I'll go back if I can. No, I can't go back. Oh, no, I can. Yeah, 10. Yeah. Let's have a look at the next example. No?
No.
Hold on. There. Right,
The
so
question you asked for the distance, right?
yeah, the height. Let me double check. My question was, a small satellite in a parking orbit around the Earth. How far is it from the surface of the Earth? Note the radius of the Earth is that, and the mass of the Earth is 5.97 times 10 to the power of 24 kilograms. Okay.
Save it.
Hmm? I'll save it, don't worry. Oh, don't you worry. Right, next. The planet Mars is observed to be on average 228 million kilometers from the Sun. One Mars year is actually 687 Earth days. Using this information, approximate the mass of the Sun, approximate the speed of Mars, and then there's the last part here. Okay, so just write down the information. You can draw it if you want. So I just want a diagram or the information to be noted. So you know the distance between Mars and the Sun, and you also know how long a Mars year is. It's 687 Earth days. Got the info? Okay. So let's have a look at this. So here is the Sun, and then here is Mars, and Mars of course is going around the Sun. Now it's not going around in a circular orbit. What type of orbit is this? Elliptical orbit. But we can say it's roughly a circle. What's the time taken to do one orbit? It's 600 and...
80.
Guys, just look at what you wrote down.
I say 87.
Yeah, but not with confidence. 687 days. And we also can measure from our telescope the distance here, which...
How do you do that?
How?
How do you measure just by looking?
Laser by laser.
No, just use your... Remember in semester 1 we did trigonometry problems using sine and cosine rules? So do you remember from just using a telescope, we can measure the height of a building? So what you can do is you can stand at one part of the... Well, here's the Earth here. So you can stand at one part of the Earth and measure the angle to the Mars, and then at the same time on a different part of the Earth with the distance between them, look at the same planet, and from using the angles you can, and using this distance here, you can know how far away Mars is. We did this in semester 1. And also you can estimate the length, the radius of the Earth by climbing at the top of a mountain and measuring down the angle. So you literally just need a telescope and a meter stick, and you can measure how far away Mars is. It's not difficult to do, and the distance has been known for a long time, hundreds of years. So the distance is something which is easy to know. Also, again, just by looking, you can know how long it is for one orbit. Again, just by looking. So what did we say the distance was? 228 million kilometers. So that's 10 to the 9 meters. Now, I want you to appreciate what you're doing here. From just using your eyes and maths, you can know something which would seem impossible. The mass of Mars. From just using a telescope, you can know the mass of Mars. Because from Kepler's law, you know that T squared is 4 pi squared over gm or cubed. So therefore, sorry, not the mass of Mars, I mean mass of the Sun. So you can know the mass of the Sun, that's the big M here. We can rewrite this as M equals 4 pi squared or cubed over over gt squared. So if I put in the information, let's see what I get. 4 pi squared times 228 times 10 to the power of 9 cubed over 6.67 times 10 to the power of minus 11 times the time squared, which in seconds, 687 days, 687 times 24 times 3,600. And you get 1.99 times 10 to the 32 kilograms. And if you look this up, you'll get an answer roughly like this. This is the mass of the sun.
Did you change the days into
Seconds.
You change it to seconds.
Oh yes.
The mass of the sun you gave us before was 10 to the power of 30.
but still different?
10 to the 30? Are you sure?
Yep.
Or maybe, did I write 228, or maybe I should have written 2.28. Am I off by 100, is it? What did I say the mass of the sun was?
1.99
1.99.
times 10 to the power of 30. Sorry.
No problem. I'll check that now. 4 pi squared over 2, maybe I'm missing a... I'll check it right now.
I think it's 1.989.
Yeah, mass of sun. Let's have a look at it.
Million is not 6.
It is 6, yeah.
You wrote 9.
But then that's million kilometers.
10 to the power of 30.
Where's mass? Goodness sake, just give me mass.
There's an error there.
Distance.
Where?
Mass 1.98855 plus or minus 0.00.
Hold on, would you? For goodness sake, just give me the mass. Stupid Wikipedia. Just tell me the mass of
Just
the
search in the
sun.
Google, they will give you a book.
No, it didn't. It didn't. Oh, maybe in Google. Okay.
Yeah, Google
Not Bing. Right. Mass of sun. Yes. Okay. So I think it's my distance that's off. Distance between sun and Earth. 149 million kilometers. What did I say?
2 to 8 million.
228.
That's so big.
So
Oh no! Wait. Hang on. That's Earth. I should be looking at Mars.
yeah.
Distance between sun and Mars. 228. Is that what I said?
Yeah.
So I must. Right. Okay. So maybe I hit something in wrong on my calculator. 228 million kilometers. That's what it said, isn't it?
Yeah.
Million kilometers. Million is 10 to the 6.
Yes.
Kilometers is 10 to the 3. Together that's 10 to the 9. And it's cubed over G. Oh, maybe I didn't. Wait. Come on.
2.8 times.
Hold on. I think no, I didn't. I did remember my square. 1.99 times 10 to the 32.
I've got 1.14 times 10 to
I'm off by exactly 100, which means one of my decimal places is wrong.
Yes.
Check your time.
My time?
Yeah.
I typed in 687.
Yes. Yes.
I typed in 360, not 3,600. I lost a 0. 1.99 times 10 to the 30. That's much better. look at how good that estimate is compared to the true value. The true value, here, look, 1.989, and I got 1.99, 10 to the 30. So it's quite good. What's wrong?
See,
Yeah? What? You asked me to find out where the mistake is.
no, because I checked.
No, what do you ask me?
Yeah.
What do you ask me? Find your mistake? No, I found my own mistake. You find your mistake.
I just checked the same value 3 times.
You forgot there's 24 hours in a day. Move back. Okay. Where am I next now? Right. What is the speed of Mars? So we've seen one like this before. We have, what can we say? F equals gmm over r squared, and F equals mv squared over r. By making these equal, we can get gmm over r squared equals mv squared over r. Small m, r and r. So I can get v is the square root of g m over r. Do we know the mass of the Sun? We do now. So square root 6.67 times 10 to the power of minus 11 times the mass of the Sun over, now what did we say the distance between 228 million kilometers?
Yep.
0, 0, 0, 0, 0, 0, 0, 0, 0. So you get a speed of 24134 meters per second. Okie doke. Right. C, last part for this one. It is. What was it for Earth? I don't remember.
24.
What was it?
Or the
29.7 kilometers per second.
Oh, we did it in kilometers per second, did we?
Yeah.
Well, this would be 24 kilometers per second. 24.1. What was Earth? 29.
9.
Okay. Okay. So Mars not moving as fast. Okay, C part. So the orbit of Mars is not circular, it is elliptical. At its nearest to the Sun, it's 207 million kilometers away instead of 228. What is its linear velocity? Okay, so if we go back here, so here, when its radius is roughly equal to the radius I gave you, which was what, 228 times 10 to the 9 meters. Its velocity is 24.1 kilometers per second. But of course, it's not a perfect circle, so maybe I'll make this distance look a bit shorter. Here, there's Mars there and there. Here, its distance is only, what did I say in the question? 207 times 10 to the 9 meters here and here. But however, you know from Kepler's law that although they're
different length.
although different lengths and different speeds, they still produce the same area. So what we need to do is get the area. Now I know it's not exactly a perfect triangle, but we can roughly say it's a triangle. So if you look at this triangle, do you know? Okay, well, what unit of time should we use? Your question yet?
We can use sector formula.
No, not for physics. No, we want to keep it simpler than that. Yeah, but you could, but we won't.
Because it's a big awesome.
Yeah, but we don't need to be that accurate here. Okay. Right, so it's going to be a triangle. What unit of time should we use?
Second.
Well, yeah, since let me just fix my writing pad here. Since we're already dealing in seconds, we might as well stick to using seconds. So in a 1 second interval of time, in the black triangle, we know the two radii, they're both the same roughly, 228 million kilometers, and we know how fast it's going per second. So in 1 second, how far has the planet moved? 24.1 kilometers. So you could make a triangle where you know the three sides, and you can get the area.
A should be the same.
And likewise, on the other one, the area should be the same. But you don't know the distance it travels because you don't know its speed. So what I'll do, I'll draw my two triangles. The first triangle, you know that this is 228 times 10 to the 9, and this is 228 times 10 to the 9, and this is 24.1 times 10 to the 3 kilometers. Now we need to calculate the area. Now the formula, we don't know any of the angles. Yeah, we could say half the base by the height, but we don't know the height. But what we could do, equate what?
Both triangles.
No. What we need to do here is, I think the easiest thing to do would be to make a right angle triangle here. So we can use Pythagoras to get the height here. So if I call that h. So from Pythagoras it'd be square root 228 times 10 to the 9 squared minus 24.1 times 10 to the 3 over 2 squared. What?
What do you use for the base?
Half of this.
That's with the speed.
Yeah, but we're looking at per second. So after 1 second it's moved that distance. Right, so Pythagoras gives us the h. Square root 228 times 10 to the power of 9 squared minus 24.1 over 2 so the height here I got is 2.28 times 10 to the 11. So the area is half the base by the height, and this is the base. So if I do that times a half times, so my area will work out to be a large 2.7474 times 10 to the 15 meters squared.
We use the half of 2.24.
I used half of 24.1. I'm getting the whole area. Yeah. Yes. Okay, so I have the area. Now I can look at this triangle. So I'll draw this triangle. We know this side is 200 and, what did I say? 8, was it?
207.
207? 207. 207 times 10 to the 9. This is 207 times 10 to the 9. This x we don't know.
We know it's 24.
No, we don't know this x on the other triangle. That's actually what we want. We don't know the height, but we do know what the area is.
So we can.
Yeah, and actually let's get the height first. So from Pythagoras, height squared plus x over 2 squared equals 207 times 10 to the 9 squared. From Pythagoras. H squared x over 2 squared equals this squared. So I can say h squared equals 207 times 10 to the 9 squared minus a quarter x squared. So h is the square root of that. So you know that area is half the base by the height. So 2.7474 times 10 to the 15 is a half the base by the height. So although it's ugly, it is quite ugly, it's still just an equation with x to solve. So we can solve this for x, but we'll have to do something first to it. What should we do first to it? We should square it, shouldn't we? To get rid of the square root. So to save me writing all those ugly numbers, okay, I don't like ugly numbers, I'm going to call this ugly number A, no, not A, alpha, and I'll call this ugly number here, after I square it, beta. Have you got that? So I have here alpha is a half x square root beta minus a quarter x squared. And I'll get back to alpha beta later. Right, alpha squared equals a quarter x squared.
Wait.
Beta, yes?
Where did you get the half x squared from?
What half x squared?
In the alpha part.
The alpha. This half x. Half the base by the height is the area.
But I thought we already had the area, like we knew it already.
We do. It's the alpha.
I get you.
Okay. Right. So what this equation isn't too bad. You get alpha squared is a quarter beta x squared minus a 16th x4. So if I multiply by 16, I get 16 alpha squared equals 4 beta x squared minus x4. So I get x4 minus 4 beta x squared plus 16 alpha squared equals 0. Now what type of equation is that? It's a quadratic, yeah, where you have 1 x4 plus some number x squared plus another number equals 0. So I should work out now what minus 4 beta is and what 16 alpha squared is. So I need to plug in my numbers. So beta is 207 times 10 to the power of 9 squared times minus 4. So I get an ugly number here, minus 1.71396 times 10 to the 23. Now I have a 16 alpha squared, so 2.7474 times 10 to the 15, that's that, squared times 16. So here we get another ugly 1.2077 times 10 to the 32. Right, so if you use your quadratic formula here, we get two answers for x squared. X squared equals 1.7 times 10 to the 23, or x squared equals 7046255546. Now one of these answers is to be rejected. Which one do you think is the one to reject?
The one with the minus.
Both are plus.
The smaller one.
Now remember, x represents the distance it travels in 1 second. So x is actually the velocity in meters per second. So which one do we reject?
The smaller one.
No, the bigger one, because we must reject this one, otherwise our planet is going faster than the speed of light.
No, I meant the answers are set.
I said which one do we reject twice, and twice you said the smaller one.
We've been in distance for 4 hours.
Yeah. So this is the one we take. So we get x equals the square root of that number, 7046255546, and we get 26545, or x, which will be v in meters per second, sorry, kilometers per second. What did I get previously? Yeah, great, that's a great answer. V equals 26.5 kilometers per second.
An exam question?
Could be. No, it'd be a section B question. So, when our first answer for the V was, I think, 20, what was it, 29? Or was it?
24.
20, no, 24
Yeah,
kilometers per second. When the planet was nearer to the sun, what happened to its velocity? It increased. So it could sweep out the same area. It needed to be going faster. Now this is different to circular motion because in circular motion, the speed is constant in circular motion. In elliptical motion, the speed is not constant. It's traveling faster when it's nearer to the planet, the sun. Okay? So, it is actually a big difference if you think about it. At one part in its journey, it's going at 24 kilometers per second, and in the later part of its journey, it's going 26. Don't pack up, Gerard. Take your stuff out. Not finished. Take your stuff out. Yeah. In the exam, I don't think it's likely that this will come up. I would say it's unlikely to get one like the example I just did, but it wouldn't be completely impossible. However, if the question did come up in the exam, they would help you out a bit more by giving you diagrams. So for example, if this was an exam question, what they would do is they'd have a picture of the planet and they would draw the two triangles in for you and they would say something like the areas are equal. But I don't think they would do this on the exam because the physics exam, I noticed they try and limit how much maths there is in one question. So I feel like if this wasn't the exam, it might be a little bit too much maths. And if it was in the exam, it'd probably be split up into two parts maybe. But still, it's not completely impossible to be in the exam because this is my problem. Let me show you here. Well, no, I won't show you, I'll just tell you. The syllabus says students need to use Kepler's second law in the exam. However, I'm not sure if that's a mistake because who would teach you Kepler's second law and not the first and the third law, you know? So I'm not sure if the syllabus meant to say students need to use Kepler's laws. So there is a small chance you could get this in the exam. They haven't asked it before, but I want to cover every possibility that they could have in the exam, okay? So if you found this a little bit difficult, that's okay. It's probably not going to be on the exam. No, actually, I don't think it's that bad of a question. Okay. Let's have a look here. Sorry about that. It's loading, don't worry. Close this, maybe.
Too much on RAM.
Too much, yeah.
1 GB.
There we go. It's loading. Let me free up some RAM here.
Bring your laptop on.
No.
What?
No, never. Right, can I close this notepad? Let's try and free up all my RAM. Oh, come on. Well, actually, maybe there's something wrong with the last page. Oh. And let me just open up the page again. You're not going anywhere till you get your homework. We have one more physics class or two? What?
One.
When?
Tomorrow.
It's tomorrow? Are you 100% sure? What time?
11.
Oh, that's right.
No, we don't.
Yeah.
Yeah. Tomorrow?
Yeah, tomorrow.
No.
Do you have the special timetable for next week?
Yes.
Yeah, this 11. Is it?
One sec.
That is for take two.
Your intake. No, this is IFY September engineering. Monday quadruple, and then Tuesday 11 o'clock. Then you have maths, and then there's a maths again with me on a Wednesday. Right. So what is likely to happen is we'll finish up the fields tomorrow. Then let me just see why this last page didn't save. Are we saved? Yes, we are. Okay.
Just have two maths with all these. Three maths actually. Four.
It's increasing as time goes on, huh?
This is four.
There we go. One question for tomorrow. From an observatory on Earth, Mars is observed as having two moons. One of the moons, I think that's two moons actually.
Yes.
Yeah. One of the moons, well, y'all watch The Martian. Is that two moons? Yeah. One of the moons called Phoebus is observed as orbiting Mars at a distance of 5989 from its center kilometers, and its orbit takes 7.65 hours to complete. Finally, the radius of Mars is estimated as 3,390 kilometers. NASA is planning on sending a small 100 kilogram probe to Mars. Help NASA out by answering the following questions. You may assume a circular orbit when necessary, although this is an approximation, it is a good one. So firstly, estimate the mass of Mars. So you can use Kepler's Law there. Do you have the radius of the moon? You do, don't you? The orbiting radius. What are the moons? Yeah, and do you know the time? You do. So you can estimate the mass of Mars. You can also estimate how fast the moon is moving. Here I tell you that the radius can vary by up to 10%. What is the fastest and slowest speed it will achieve? So part C is like the question I just did, except you need to do it in two halves. You need to reduce the radius by 10%, it'll make it go faster, and increase the radius by 10%. What will happen to its speed? It will go slower. Approximately what is the density of Mars? Approximately what is the gravitational field strength on the surface of Mars? Approximately what is the radius of the parking orbit for the probe around Mars? Approximately what is the gravitational field strength on the probe when it is in a parking orbit? And approximately what is the potential energy of the probe while it is in a parking orbit of Mars? So I know it seems like a lot, but this would be, a section B question for sure, where they have these multi-part stories. So it'll probably, I'll probably use most of the class tomorrow doing this question. If there was time left, I can show you the exam question which is like this, because I remember there was a Mars question a few years ago. So I want this whole question done for tomorrow. Now before you think about saying you can't do it, listen carefully. Part A, I already did an example of that. Remember where we estimated the mass of the Sun. Part B, I already did that twice. The speed of Earth and the speed of Mars. So you have one example of A, two examples of B, one example of C. Part D, what's the formula for density? Do you know the mass of Mars?
Yeah.
You will at that point. Do you know the formula for volume of a sphere?
Yeah.
4 over 3 pi r cubed. Do I give you the radius of Mars? I do. So you can do part D. Part E, I've done already. Part F, I've done an example of already. Part G, I've done an example of already. Part Well, the only difference in G was for the airplane, which was 10,000 meters. Take this seriously, Yanni. I want this done tomorrow. I'm going to check. KJ, you too. I'm checking tomorrow, and there'll be big trouble for anybody who comes to class tomorrow without this done. And H, potential energy, I've done as well. So each one of these questions, there is an example of this in your notes. So there's zero reason for this not to be done. There are examples for every part here in your notes. There is absolutely no reason for this to not be completely done perfectly tomorrow. I will check it tomorrow. And I think if it's not done tomorrow, we'll have to arrange meetings with you and Connell, or you and the principal when she comes back, okay? Because I'm not going to tolerate this not doing work anymore. It's not something that I'm going to tolerate. So either have this done or don't. Both are your choices. Just keep in mind that if you have it done, everything will be okay. And if you choose not to have it done, which is your choice, everything will not be okay. Think carefully about that tonight when you decide, should I go to Pizza Hut or should I do my homework? Just keep that in mind when you're making that choice later. Or Domino's, whichever you prefer. Okay? Right, so if you need to take a picture, or are you just going to get it from the video?
Video.
Well, I'll leave it there for a minute. Just physics tomorrow, no maths, or
Physics and math.
but not back to back.
No.
After lunch is the maths or something.
Ah,
See you.
see you all. See you tomorrow.
Can I close this?